Good morning, everyone. My name's Will. I'm one of the mechanical engineers at ANSHM. And today I'm going to be talking to you about a water pipeline project that we have recently done and is still ongoing. So pipelines can be a little boring, right? They're pretty simple and they don't move much. They stick around for a while, but sometimes things go wrong, and as John alluded to, we can have some big problems that arise. So our client came to us they wanted to know more about the bending stresses throughout their pipe and the vertical loading on the supporting sills. And they tasked us with instrumenting the pipe and with the main deliverable of coming out with live bending moment diagrams. So to come up with how we're going to do this, we need to stick with a model of how we're going to do this. How are we going to come up with a way to input the data that we could get and have an answer that we could give to the client. Now, we needed a model to firstly find the initial loading conditions of the pipeline, and then we wanted to combine those initial loading measurements to, well, not measurements, but initial loading conditions with the loading changes that we measured, feed that back into the model and come out with something that we could compare to actual measurements as well. The intent with this is to automatically feed everything in and have a nice, pretty picture for the client to see at the end of the day. So the model that we used was a continuous beam for the pipe. We actually used a Python package that Colin made and was so kind to leave open source called PyCBA, which is the continuous beam analysis. We modeled the pipe to have fixed supports at the piers, roller supports at each of the sills, and at the expansion joint is a hinge joint. The loading was a distributed load that was made up of the mass of the water and the pipe itself when the pipe is full of water. And to set the initial conditions, we assumed that there was zero displacement at each of the nodes. Now, before using Colin's software, we wanted to validate that we were actually using it properly. So we did a FEA, made the pipe in a similar fashion with the same conditions. We used some survey results that the client fed us and outputted some vertical loads at each of the sills. Then we used those vertical loads, put it back into PyCBA, and just checked that we got the same bending moment diagram and the same deflections to be output. So we checked that we were doing things correctly. Now, it should be mentioned there was a lot of assumptions made to do this, particularly uniform pipe stiffness, a uniform cross-section. There's no additional loading from solar and thermal effects. There's a bunch, and this is pretty important to consider when you see where I'm going with this. Now that we have the model, we now need to do the measurement. And to get as much data as possible, we instrumented the pipe with a range of different sensors, mainly strain gauges and tilt sensors. And it was also discussed and decided that using off-the-shelf sensors for the rocker plates themselves was not going to be optimal for what the client wanted. So my colleagues designed a bespoke wireless sensor node system that was comprised of tilt, temperature, axial strain, and internal humidity sensors. And here's a little bit more about that hardware. There was a fair bit of testing that was involved as well for the strain gauges, testing different adhesives to see what would have the best thermal stability given the temperature variability of the environment. There was testing of the communications and how far we could get with the wireless nodes. And also for the tilt sensors, there was drift, accuracy, and thermal stability tests as well. And this is what they look like installed. So there's 2 sills on each side of the pipe, on the left and right, and we take those measurements and combine them and throw them into the 2D model. So it's the combination of each side. Now, all these sensors feed into a base station, which eventually goes into to our server, where there's a database that handles a lot of the processing and analysis, and then eventually gets fed up to the client on an online data portal that they can access, and they can see all the data quite easily. And this is the results of the measurement side of things. Now, all looked pretty good. I'll touch on that big drop in the middle there in a sec. That's actually a dewatering event. So when the pipe's been completely cleared of the water. And this is our way of validating that what these measurements that we're getting are actually realistic. So there was some calculations that were made doing the massive what kind of loading drop you would expect when you rid of all the water in the pipeline. And we compared this to what we were measuring, and clearly the results that we're seeing are at least somewhat realistic. So we have a model that seems to work and some measurements that also seem to work. So everything looks great, right? Not quite. And this goes back to John saying, how hard can it be? And, just quite funny that when he procured this project, he goes, how hard can it be? And then goes away mountain biking for a month and leaves it for the rest of us. And yeah, everyone in the office kind of learned quite quickly how hard it kind of can be. You get a simple problem, or a seemingly simple problem, and you set up these conditions and the engineering principles behind it. And when we do the sum of forces and the sum of moments, the predictions of the loading and stresses that we see far exceed what we actually measure next to the pipe. So there's clearly a problem here, most likely with the model, and it seems that the measurements are what we should expect, but the model is not constrained well enough, and clearly one of our many assumptions that we've made along the way is preventing us from being able to properly model without having the measurement come in and double check everything. So how hard can it be? It's harder than you might think sometimes. And what we're doing now is essentially collecting more data. We're trying to improve the model and trying to improve the complexity of it by considering things like solar and thermal behavior, as well as rainfall behavior and the effect of the soil moisture on the supporting sills. And we're also coming to people like yourselves to try and approach things in a collaborative manner to try and see, what do you think we're missing? What do you think that there is that's left to do for this? Yeah, that's about all.
Thank you, Will. We're just going to push all questions to the end. We've got a discussion session there. But the point here is, what a leaping, if you're going to do some research and you're an early stage researcher or even a late stage researcher, jumping in at this point is a way down the field, and writing papers and having insight with impact is easy from here, or easier.